Good morning. We have the pleasure to have today Helder Larraguivel from Warsaw University, where he's working with Piotr Zukowski. And Helder will tell us about connections between random matrices and criticality series, especially some exact results. Please start.
So, thank you very much for the introduction and for the possibility of being here. I would like to, in advance, say a disclaimer. So, I know in the abstract I wrote that I will be showing some relations to some formalism called topological recursion in random matrix theory. Well, it's much bigger than just random matrix theory. Still, I realized that just explaining the derivation and full scope of this formalism, it's too long and too nasty to just 150 minutes of presentation. So the disclaimer would be that I would skip that and stick only to more simple and general examples between random matrix theory and two-dimensional CFTs. And if anybody is really interested in topological recursion, which is just a perturbative solution to that sort of constraints, I'll be more than glad to explain that separately or maybe in another talk. But yeah, that's pretty much it. The rest stands, and well, without further ado, I would like to begin with one question, because I don't know 100% sure the background of the audience. So I would like to know if everybody is slightly familiar with some basics of two-dimensional CFT. Say, what is the Witt algebra or Virasoro algebra? Does that ring any bells? It's alright, you don't have to. Actually, that's what I also came prepared for let's say, a brief introduction to just what we need to match these ideas between random matrix theory and two-dimensional CFT. So I guess I'll just go through this quick recap. But let me just begin with some other interesting things and basically just some motivation. So most of what I'm going to say can be easily found in this one paper by my supervisor, Professor Piotr Zukowski from the University of Warsaw. It's a collaboration with Masahito Manabe, one of his postdocs. It was published in 2015, replaced version 2017. And basically, the name of the paper is Quantum Curves and Conformal Field Theory, where everything that I'm going to say can be easily found there. And well, I'm still working in some generalizations to that, so that's part of my PhD project. Nevertheless, all references that is included in this paper fully cover everything that you need to be familiarized topological recursion to the CFT, random matrix theory, and so on. So this is the only reference that I'll provide. Reference therein, like I said, complement everything. So the motivation would be why are we interested in random matrix theory, or matrix models as so called in quantum field theories? So basically, this happened to appear as in various areas of mathematical physics, almost too simple, but not so simple enough to capture a lot of properties about, let's say, we'll go first with zero-dimensional non-abelian gauge series. To pop out, oh, my bad. Here it is. As one-dimensional wave functions for some integrable many-body quantum systems. Basically, if you try to solve some system named Calogero-Moser system. It's a one-dimensional many-body particle physics, many-body particle quantum system. It turns out that you can describe the wave function as a matrix integral or random matrix integral. They pop out in two-dimensional CFTs, or conformal field theories, which is basically a very good example, 1+1 quantum gravity. They also appear as in string theory. And jumping from 0, 1 to 4 dimensions, they happen to appear in supersymmetric gauge theories after performing something called localization. So I know probably you heard plenty other appearances of random matrix theory in statistics, in chaos theory, so on and so forth, but this is one of the reasons why we're interested in them from the point of view of quantum field theory, because we're interested in deriving non-perturbative effects for partition functions, and matrix models turn out to be simple enough to be able to derive some information, but yet not so simple to be also useful. Well, like I said, it's 0 dimensions. Well, many physicists would say, I can eat 0 dimensions for breakfast. Come on, we live in 3 dimensions. What are we interested in 0? Well, the point is that in 0 dimensions, things simplify drastically enough to be able to solve the theory and derive some important results, but yet there's still some degree of difficulty that makes it non-trivial. And basically one can see the appearances of random matrix integrals in this and many other areas, so this is one of the main reasons why we're interested in studying them. Okay, having that said, moving on to this short CFT. So basically, one of the simplest ways I like to see or think of the appearance of conformal invariance into a matrix integral, it's not even think about a matrix integral itself. So if I give you just a Lie algebra of generators saying that they satisfy the following, this is known as the Witt algebra, which can be thought as the Diffie-Hellman algebra and so on. And this is just an abstract Lie bracket. So it doesn't tell you much about the physics, it doesn't tell you much about the geometry or what we're doing. But a very simple and important representation of this algebra is the following. So basically this is a generator for n bigger or equal than -1. And it turns out that you have infinitely many of these generators, so this is an infinite dimensional Lie algebra. This is one of the big important things when it comes to CFT. Two-dimensional field theory, it's invariant under this algebra, and since you have an infinite number of generators, you have an infinite number of conserved charges, and that's what fully allows you to constrain the whole dynamics of your system. So that's why they're in 2 dimensions. The CFTs are integrable systems. And one way to see the appearance of this guy, well, so this is a one variable representation. How about, well, let's first just say, imagine that we have a function which is analytic. And we represent it in this way, just as a Taylor expansion, say, where Tn are some coefficients not given, so any analytic function can be recast in this form. And we can see very easily that if we have Ln acting on the exponential of this function, still arbitrary analytic function, we get, well, very easily x n plus 1 b prime of x e vx. So this is a very simple action, but noticing that if we take them to these t's to be variables, we can also differentiate with respect to them. And differentiating with respect to these, it's very obvious to check that basically we get xn evx. So, well, everything seems trivial so far, nothing very exciting going on, but then it means that if this is a power expansion for this function, we can accurately represent this as operators acting on the t variables rather than the x variables. So we're going from a one variable representation to an infinite variable representation. So in the end, this L operator acting on this particular vector, which is very general because it's just the exponential of arbitrary analytic function, can be recast as so it turns out that you can see, well, basically, this generates some symmetries, or, well, not even just say symmetries, this generates some transformations. This generates some transformations on this function, and you can recast them entirely in terms of transformations on the time variables. So, long story short, it turns out that if you exponentiate for an arbitrary real parameter this and apply it to this vector, what you get is E x 1 minus P n xn minus 1 over n. And basically this is the transformation they generate. But if you try to see how this transformation acts on the time variables, you will end up seeing that if you put this back into the form of one infinite sum power series, you'll see that the time variables are transformed. If you think of them as a vector, an infinitely long vector, basically you'll have something like this. So you have the same group action now instead of the variable x on the times, but the same basically structure. So they both generate the same transformation but in different representations. And if you want to find out these generators, what form of the matrix they take, well, basically, if you decompose them in its in a certain basis, well, the natural basis, you will end up getting so this is a very simple matrix where S and L go from 0 to infinity. So those are the values that are allowed to take. And as remember, n goes from minus infinity to infinity. So I claim that you most likely have seen these matrices at least once before. Any idea where? Exactly. So the harmonic oscillator, you remember you have this A dagger, and n operators, right? So if you represent them in the eigenbasis of this operator, you get that n is just basically 0, 1, 2. A is basically 0, 1, 2. And a dagger is just basically 0, 1, 2. So you can already see the appearance that actually this is a very interesting subgroup, that L minus 1, L0, and L1, they generate basically the SU2 algebra. So this is a subalgebra of this bigger width algebra that I was talking about. And you can already see that, well, this width algebra can be entirely mapped through this change of representation from an algebra acting as on operators on one variable to an algebra of infinite matrices. And in the end, well, straightforward to see that this is GL infinity R. So basically, this algebra, it's identical or equivalent to this algebra over here. So this is some of the very basic things about conformal field theory. Now I'm going to see how this very simple sketch relates to some very simple integrals, and then forward to matrix integrals, and in the end how to use the power of some of these infinite generators to fully constrain the solutions of some random matrix integrals. Any questions so far? It was very simple, right? So I have a question for you then, if you don't ask me. So that's the way it goes. If I change the order of these generators, let's say it's not normal order anymore, is it the following form, or do I still get the same algebra? Do the Lie bracket still holds the same, or does it change? Now you seem very puzzled. Just go with your gut reaction. This is not a test, so I'm not taking any scores. You won't fail, you won't pass.
Change?
Why?
I don't know. That was a guess.
Okay, so basically,
Put it there and do the calculations.
yeah, actually it's very simple. You can put it there, do the calculations, and show that the algebra won't change. And this is not a peculiarity of this function. It happens for any function that you put here. If you reverse the order, the algebra is still the same, but the main difference is the group it generates. It's slightly different. So let me show what is the difference. So like I said, since we know already what transformations this guy produce, we would like to know what transformations he produces with this extra factor here. And well, you can sit down for 20 minutes, maybe half an hour if it's the first time. Use this Baker-Hausdorff, Campbell, I remember the whole tree, formula, work out the commutations between this one and this one. You see that most of them just simplify because there would be zero. And in the end, you get an infinite sum. You see what it converges to, a logarithm, blah, blah, blah. But basically, if you exponentiate and apply to an arbitrary function, you'll see that you'll get this thing. So this is the same action as we had before, but we have an extra factor. This is an overall factor produced by this shift we include in our generators. And this overall factor can also be recast as an operators acting on the time variable, so this t's. And since it can be recast like such, it can also be seen as a matrix transformation. So it's a linear transformation acting on these t variables. And what kind of linear transformation? Well, basically, if you substitute here EVX, and here having EVX, you do the same trick. So you just pull this on the exponential, take its Taylor expansion of this function, which is rather simple, which it would be just a logarithm, and notice that your new variables would look, will have the following transformation. So it's basically still a linear transformation, so you have an infinite matrix plus some translation. And this translation also depends on p, but it's basically generated by the expansion of this function and the exponential. So changing the order, you still get pretty much the same group, but not quite. Now these generators belong to, any ideas? If the other ones belong to GL infinity, these ones belong to affine GL infinity, right? Excellent. So you have affine, oh, sorry, this is the group. So you have GL infinity over the reals, and this is the affine version. Why? Because they produce this extra translation factor. So this is the only difference when permuting the variables, how they act on the times. Oh well, this is basically pretty much all that we will need to see how this infinite algebra actually appears in places where you have used it before, I'm sure of that, but never really thought of it this way. So one of the ways you can think of is this factor over here. Basically can be think if you say y will be x1pn xn, basically this argument, you will end up e by times dy dx. So this is the transformation this one generates, and since we would like to have everything in terms of y on the right hand side, we will just set dx epl affine evx ey dy. So if this, so now we have introduced this differential. So basically these are now forms, or just we're ready to integrate them. So this is basically telling us that the way we transform the differential of this guy, including this dx, would be to include what comes out of differentiating would be this factor over here. So this tells us that if we want to do this sort of transformations on this function, we'll need to include the action of this differential, which is encapsulated here. And well, since like I said, this is a differential, we can put it under the integral sign, and we'll see that if you have the x e b of x, well, this is an integral, but if you put here this generator dx x of n plus 1 e v of x, basically what is this? Well, you can integrate this very easily, just evaluate at the boundaries, so the fundamental theorem of calculus, and you say, or you assume or work only with potentials that suppress all these polynomial factors at infinity. So we need to, well, not only at minus infinity to infinity, could also be from 0, or this works even for arbitrary domains. But if you want to equate this right-hand side to 0, so this left-hand side to 0, the easiest way is to integrate over the whole real line. So once you do that, you'll see that, aha! So this looks pretty much like my Ln generators, but the affine ones. So what is this telling you? Okay, this is under the integral sign and it's in terms of x variables, but we can put it in terms of t variables now. So we can still produce this same identity, but now in terms of t variables, acting on this integral. And set it equal to 0. So basically, after we integrate with respect to x, we have a function in terms of these t's, which is in terms of infinitely many t's, but we have constructed an infinite family of operators that annihilate this function. These are basically later on going to be called Virasoro constraints for the matrix integral, but this is just the baby version, one-dimensional way of thinking of them. So in other words, you get some recursion relations for the moments, because after you put this, well, if you write the moments in the following form, let's say n plus 1 xn plus xn plus 1 b prime of x. Once you expand this differentiation over this and this is what you get. And if you think of it as the moments for this probability distribution, basically you get some recursion relation set it equal to 0. So what I said when I said that I claim that you've seen these recursion relations, I mean it, because these recursion relations, when you specify v of x to be minus t of x and set the domains from 0 to infinity, these are the recursion relations for the gamma function. When you set b of x to be minus x squared divided by 2, when this is a Gaussian, these are the recursion relations for the Hermite polynomials. So basically, this is another way to think of them, that the recursion relations can be thought as infinitely many operators generating this algebra, but now you can recast them in terms of these t variables. So far so good? All with me? Okay, so now moving on to matrix integrals. So I'm just going to start, this going to be, in a particular case, definition of the matrix integral. Okay, so this is not exactly the matrix integral, but because you notice that there's this factor for those who are very well acquainted, but this factor can be thought of just the characteristic polynomial of the matrix raised to a certain power. These z's are going to be the eigenvalues of the matrix. This would be the potential defining our ensemble. This is the Jacobian factor. Beta determines whether if it's symplectic, quaternionic, unitary or orthogonal. And this prefactor is just, well, because it would help us do the math at the end of the day. But it's basically an overall factor which can be included or excluded. So you'll notice that we can do the same trick as we did before. We can insert this operator we need to sum over all variables now because this is an n variable problem. But instead of writing these terms one by one, I'm going to encapsulate them, all of them, in just, let's say, one generating series, which is of this form. If you expand this in terms of powers of z, you get all the moments. And also, for those of you who are a bit more familiar with matrix models, or just matrix in general, this can be thought as a resolvent of the matrix. So given this idea, we can equate this to 0. And we can also expand. So basically, differentiating over each and every one of these terms, we get so this is what we get. Long story. Oh, yeah, sorry. I forgot to define that I'm taking this omega y to be basically just the resolvent. Without the 1 over n factor, I'm being a bit sloppy in notation, but everything just holds. So, likewise, you can fully encapsulate this as some recursion relations. Actually, the topological recursion appears as a large n solution when you do this Gaussian asymptotic expansion to this set of equations, solving them recursively one by one, and noticing that the diagrams have certain topology associated to it, blah, 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 and then you name it topological recursion because of the topology of the diagrams. But anyway, long story short, this is just some recursion relation which can be associated to the similar operators, like this. They still define an infinite algebra, and you can think, probably you have, I'm not 100% sure if you have, at least for the first one of these recursion relations, you can think of them as the Schwinger-Dyson equation, or aka in quantum mechanics also the Ehrenfest Theorem, saying that if you start from a path integral formulation, basically, this is the form of the Schwinger-Dyson equation, telling you that after applying this operator here, you will get, surprise, surprise, well, not so much of a surprise, right? That if you extremize the action and take its expectation value, is equal to 0. So basically, that the correlation functions of the correlation functions obey classical laws, the expectation values. So this is just, if you put here some phi to the n plus 1, the equivalent version to that. So this is not something just inherent of random matrix theory, but it appears in pretty much anything, either quantum mechanics, quantum field theory. You can always derive this set of equations. The only slight subtlety, though, is that since now we're working with distributions, you would encounter some Dirac deltas which identically vanish, and well, those are hard to define. But everything that I'm saying, it's perfectly legitimate or can be extended to more general QFTs. But since we're in the business of random matrix theory, we just stick to the matrix integrals. Okay. So now somebody very clever once noticed that this can be fully recast as a two-dimensional CFT theory, because I don't know, is everybody familiar with the concept word identities? Okay, basically it just says, is a quantum version of Noether's theorem. If Noether's theorem, you say you have conserved charges because of symmetries, here you have constraints of your correlation functions because of symmetries. And since the stress energy tensor, energy momentum tensor, captures all those, well, most of those symmetries, basically when you have T and taking its expectation value with whatever observables you have on the right hand side, you should be able to set that equal to 0. So this has pretty much the same flavor, the same form. So what somebody noticed cleverly is that this set of Schringer-Dyson equations, or infinite system, can be fully recast as Ward-Takahashi identities of a certain two-dimensional CFT. And this two-dimensional CFT can be thought of as a free chiral fermion, where we define it in the following way. Oh yeah. What is this curly potential I put over here? Well, basically this potential is just a redefinition to include the usual potential in terms of V of x. In terms of V of y plus alpha infinite set sum, not an infinite, sorry, sum so basically just redefining the potential to include this factor here on the top of the exponential. So if we say that, okay, this could be thought as a free chiral fermion for two-dimensional CFTs, we can construct its energy momentum tensor. And it should look like this. And if you differentiate this, square it, and add a constant times the second derivative of this, you actually pretty much have, well, you have this very same Schringer-Dyson result. Because the derivative of this, you can recast it as that. Sorry?
I noticed that you have two copies because you have 2 beta. Okay, so for beta equal to you have 4 power. So this means that you have 2 copies of you. This is what you have higher, yes? Why do you need higher? Why do you need to double number?
So in this case, once again, the full question is, since we have this beta dependence, why do we need 2 copies? Well, to be honest, I'm not thoroughly sure how to answer that, because to me, I just always took it as an initial input. But yeah, we're not trying to well, actually, it was also how it was written on the paper. But we don't need the other copy. We just stick to this part and things will work out. I guess it's just terminology from the CFT side that got stuck into the matrix model side. But yeah, honestly, there's no need for the other part. And, well, if you construct this, let's call it energy momentum tensor, this way, you see that it precisely matches this guy. And you can also find, well, this generators or modes. Oh, any other questions while I'm erasing?
So basically, I guess what you got is Schwinger-Dyson equations. This is what usually is called loop equations. Yes?
Yeah. So these are the loop equations, Toot recursion. Yes, indeed.
So what is new in some sense?
So the new, in some sense, it will come in a second. It would be basically trying to derive something from the CFT side called BP set equations. And basically for Samolozhnikov, Polyakov, and the third name with V, this one I own it to you guys. But those are PDEs that constrain your correlations that are not necessarily of this form, that actually can be fully re-encapsulated on derivatives of x. So now you avoid having n variables and recast PDEs in terms of just this one variable. And that is the main usefulness. So, okay, I think I'll just run through it a little bit. But in other words, if you expand with respect to y in terms of a Taylor series, you notice that the coefficients, you can pull them out as operators acting on the partition function of the matrix integral. And basically, well, just to give you a quick flavor of it, you can expand that stress energy momentum tensor as a Laurent expansion. Oh, maybe this one is running out. And the coefficients will give the generators for the Lie algebra, or the symmetries. And basically you can see that it splits into two parts. We're going to name the positive part as n equal to -1 to infinity. And the negative part, which is just the rest. So there is some bit of a lie when I told you that if you expand this energy momentum tensor, it would give you exactly this term. It gives you exactly this term only for the positive part. So this you can always set to 0. And these are the with algebra generators I was telling you about. But this is a whole different thing. This is a whole other set of infinite generators that do not annihilate the matrix integral, but have some non-trivial commutation relations with this. And we'll see that out of these guys, we can generate some PDEs to solve for the matrix integrals, at least some generating functions. Well, so in this case, the negative part actually looks like this. Some constant that depends on alpha, which for those of you familiar with CFT, it's usually called the conformal dimension or conformal factor, whatever that means. So basically, if you expand this, but now we're going to make a small twist. Because if you expand this in powers of y, you get these generators, but they're actually the ones we're looking for to this set of BPZ equations are expandable in, yes, let's write it in this other form. So the negative modes we find Is it still visible? Maybe this one will work. Nah, not that much. Okay. So in the meantime, just a quick recap, because I don't want to lose you in terminology. All we've done is find an infinite set of operators that annihilate the matrix integral, that one. We plugged an extra term, an expectation value of the characteristic polynomial of the matrix integral, and some parameter alpha. This parameter alpha will be important to tell us when can we derive some PDEs for this matrix integral. And yeah, well, pretty much it. So we're going to, much better, thank you. So like I said, if you expand in y around 0, you get these operators, but we want some capital Ln operators, which are expanded not at y equals 0, but at y equals x. And that's the main twist and something to keep in mind. And then, since this operator, let's call it as an operator, acting in the partition function, it splits into two parts, and the positive part that I already told you exactly matches that, so it annihilates it, and hence we only keep the negative part. So we are constructing only the negative modes, the ones that are not visible directly from tooth recursions or loop equations, and this is the main trick coming from CFT. And it turns out that this way you get, well, it is very obvious from this form now, this constant, a partial derivative with respect to x, and something b prime x squared plus b double prime x, where this f over here is a very simple thing, is so you recast this as an operator acting on the time variables, and basically, well, I can give you also the explicit expression. So inside the correlation functions, it looks like this, but as an operator on the t variables, it looks okay, fair enough. So it's been a long journey, but it's worth it. Why? Because now we at first had only these Schringer-Dyson equations or loop equations, but so basically these are hard to solve. It's a tough cookie because you have an infinite set of equations in infinite amount of variables. So in the end, you can't solve the system. It's consistent. But you don't get a simple solution as one would expect. You solve it asymptotically and compute term by term, and it's a mess. But when introducing this term over here, we are able to do some trick, which is basically, you notice that if you take the second derivative with respect to x of this function, well, basically amounts to having alpha squared omega of x squared plus alpha omega of x. So pretty cool, right? Prime. So you can almost see that it, not quite, but it resembles a lot this part. We still have to handle the other part, but apparently for some values of alpha, in terms of beta, you can fully recap this nasty guy as just simple derivatives in terms of x. And that's a good thing about it. That's the reason why we include this term, and that's the reason why alpha is that. Well, we're going to basically reabsorb this whole infinite set of equations in terms of just simple PDEs. Well, this is more or less how they're going to look. So if you multiply this by some constant C1 and try to find the constant C1 and alpha such that this derivative fully gives you this term over here, you will find out that it only works for alpha equal to 1 and alpha equal to minus beta. So this already tells you that there is some relation between the Schwinger-Dyson equations and this first equation for the generating function of moments, because if you expand this in terms of x, you get the moments of this matrix integral in terms of a much more simpler PDE. All you need to do is just specify the potential, so namely the times, to fully specify this factor, and basically just try to solve this equation. Actually, not just this, but it gives you also an infinite set of equations. Why? Because you can continue differentiating with respect to n, and well, you'll get some Bell polynomials coming out of it, but you can still match it if you try to differentiate with respect to y n times this energy momentum tensor, and then set y equal to x plus corrections. And you can find these corrections explicitly and derive an infinite set of PDEs acting on this, let's say, wave function. The reason why it's called wave function is because of the similarity between this and a Schrödinger equation. And it turns out that, well, for simple potentials, this, for instance, reduces to well-known result being, for the Gaussian, you get here the, what do you imagine? Exactly. So you get the Hermite's equation or the harmonic oscillator, namely that the zeros of the Hermite polynomials give you the moments of the Gaussian matrix integral. If you have here something more complicated, something called the Penner model, which is something like x minus log, well, I write log that way, but 1 minus x. If you fit in this potential, construct this operator, which is of this form, you'll get actually some, oh, what was the name of this? Well, you get some other set of PDEs that can also be exactly solvable. Well, furthermore, or maybe I should just round it up now. The importance of this method is that you can still generalize it. So this doesn't just hold for infinite set of times, which seems to be awfully complicated, but what we're currently working on now, or it's mostly one of the current projects that I'm going through with my supervisor, is what happens when you fix the potential, so you have a finite number of times, so you cannot represent this operator in terms of time derivatives, but include here some e to the trace of gamma m. Well, basically, when you have an external matrix source, because it will be the first step towards generalizing this formalism to multi-matrix models, which are basically appearing almost everywhere in string theory, supersymmetric gauge theories, and so on. Basically, this is one of the ways that CFT, providing these BP set equations, can help matrix model to find simple equations for the generating functions of moments. Also, one can do so for including here more variables, so x2, alpha 2. The equations should only get nastier, but still somehow manageable. Not an infinite set of equations, you have just a simple 2D PDE. And basically this is the main take-home message, that CFT helps us in random matrix theory to get exact results by giving us a set of simple PDEs, namely the BP set equations, for the generating functions of correlations.
Question, comments? I mean, I have one, because the case alpha equal 1, this is basically the case of the characteristic polynomial.
Yes.
Okay? So this means that the characteristic polynomial always fulfills some nice equation, okay, which is
Right.
which is very efficient. The case, the second case is okay. Basically, if beta is equal 1, such object is called the inverse characteristic polynomial.
If beta is equal 1 or alpha is equal
Sorry, alpha is equal
to minus beta?
Minus 1. So
okay.
Alpha is equal minus 1. Then you have you average the inverse of the characteristic polynomial, which is basically the Hilbert transform of the characteristic polynomial. Okay.
Okay.
And for example, you can see that if you would like to calculate the kernel for the model, basically you need only two of them. Okay. Just the characteristic polynomial and the inverse characteristic polynomial. So I wonder what is. So there is some kind of link between positive and negative.
Some sort of duality.
Some kind of.
Yes, there is. I didn't have enough time to talk about it, but I'm very glad that you raised the point. So I will just briefly speculate, heuristically, hand-wavely talk about it. So there's been well known that matrix integrals have dualities between them. And this is very interesting because I told you that this beta labels orthogonal, unitary, and symplectic groups, depending on whether beta is 1/2, 1, or 2. But actually, you can take beta to be a continuous parameter and think of it as a statistical mechanic point of view, kind of like the inverse of the temperature. So now we're talking that with a continuous parameter, we can do dualities. For instance, we can embed this parameter. So there's one simple duality, which is beta goes to 4 over beta square root, and you get a matrix integral which has statistically the same properties, but only at large n limit. So when n goes to infinity, you have dualities between matrix integrals, and even more interestingly, if you have this matrix integral in terms of infinite amount of times, it turns out that it's dual for beta equal 1 to something called the Kontsevich integral, which is basically e to the trace of m cubed divided by 3 plus lambda m. So these lambda are just a set of eigenvalues. This could be thought as an external field or as an external matrix. And it turns out that if you do this transformation for times going to 1 over n trace of lambda to the minus n, actually, if you start with a matrix integral of this form for beta equal 1, you can fully encapsulate the matrix integral for beta equal 1 in terms of an infinite amount of variables when n goes to infinity, obviously. So it turns out that when you have a very complicated function, you can somehow fold it into a very simple integral. So basically, this is just the matrix integral generalization of the Airy function. If you remember, this is just the, if you integrate, this is just the Airy function in terms of lambda. So one of the other things actually that we're working on is finding these dualities through this approach. Because if we know the PDEs satisfy for this, can we derive the PDEs satisfy for that via this transformation? So far we haven't had much success, but we're still, let's say, positive thinkers trying to go there. But yeah, that's more or less one of the dualities between these beta.
Okay, no further questions, so let us thank Helder again.